Hello everyone, I am Dr. Venkateswara, Assistant Professor, PG Department of Chemistry, Sri Vayan College, Narsapur. In the previous videos, we had gone through the mole concept and concept of equivalent weight and problems based on the mole concept. And in the last video, we learned mole concept in solutions, and we came to know that molarity, normality, molality, mole fraction, percentage by weight, percentage by strength, percent by volume, and parts per million. These are the units by which we can express the concentration of solutions. Moreover, molarity and normality are the two units, are the two familiar units by which usually we express the concentration of solutions, and their formulas are molarity is defined as number of moles of solute present in 1 liter of solution. That can be written as moles per 1 liter volume. Therefore, we can write molarity, we can write the molarity M is equal to moles per liter, and we can write this equation moles is equal to molarity into volume in liters, and from this equation we get the number of moles by multiplying the molarity with volume in liters, and we can convert this equation into millimoles. Millimoles is equal to molarity into volume in ml. If we multiply the molarity with the volume in ml, that can give us the millimoles, right? And normality is defined as number of moles of number of gram equivalents of solute present in 1 liter of solution. That can be written as gram equivalents or equivalents by volume in water, volume in liters. Okay, so we can write normality N is equal to equivalents or gram equivalents, equivalents by volume. Therefore, equivalents is equal to normality into volume in liters. Therefore, if we multiply the normality with the volume in liters, we can get the number of equivalents, and we can convert this equivalents to milli equivalents, that is milli equivalents is equal to normality into volume in ml. That can give us the, by multiplying the normality with the volume in ml, that can give us the milli equivalents. And moreover, we came to know that normality is equal to normality is equal to molarity into n factor. We can get the molarity value, we can get the normality value from molarity value. How can we get normality from molarity? So, by this equation we can get the normality from molarity. So, what is that equation? Normality is equal to molarity into n factor, where n factor is number of replaceable hydrogens, that is basicity or acidity of a base or basicity of an acid, and our total charge on the cations, total charge on the cations in a salt, or total charge on the anions in a salt. And coming to the oxidants or reductants, that n factor is equal to number of moles of electrons transferred. Okay. Now, I shall make an attempt to explain the applications of mole concept and concept of equivalent weight by doing some problems. So, thereby we can apply the concept, mole concept and concept of equivalent weight to gravimetric analysis and volumetric analysis. So, before we are going to solving the problems, we should know what is meant by gravimetric analysis and what is meant by volumetric analysis, right? Gravimetry. Gravimetry, if analysis of a chemical reaction based on mass of the reacting species, then it is called gravimetric analysis. I repeat, if analysis of a reaction based on the mass of the reacting species, then it is called gravimetric analysis. And there is volumetric analysis. What is volumetric analysis? If analysis of a reaction based on the concentration of the solutions or concentration of the reacting species in the form of solutions, then it is called volumetric analysis. I repeat, if analysis of a chemical reaction based on the concentration of the reacting species, then it is called volumetric analysis. Now, we shall apply the concept of mole and concept of equivalent weight to gravimetric analysis and volumetric analysis in the form of problems. And examples for gravimetric analysis are decomposition reactions, and displacement reactions. And examples for the volumetric analysis are acid-base neutralization, acid-base titrations, and redox titrations. Okay, now we shall solve the problems one by one. Okay, problem 1. 20 ml of 0.1 molar barium chloride is mixed with 30 ml of 0.2 molar Al2SO4 thrice aluminum sulphate, then what is the weight of barium sulphate? Okay, how can we solve this problem? We can solve this problem in a easiest manner, but one thing you should remind in your mind is that if you want to apply the mole concept, then we need a balanced chemical reaction. But if we want to apply the equivalent concept, then there is no need of balanced chemical reaction. Understand? Okay, if we want to apply the mole concept, then we need balanced chemical reaction. But if we want to apply the equivalent concept, there is no need of balanced chemical reaction. Okay, so coming to the problem, here the volume is given in mLs, and we know that molarity, and what is given molarity and volume in ml. What we know, molarity is equal to, or molarity into volume in liters is equal to moles, and molarity is equal to volume in ml is equal to millimoles. And of course we can write this millimoles as a weight by gram molecular weight into 1000. Therefore weight by gram molecular weight into 1000 is equal to molarity into volume in ml. Okay, so I solved this problem both in both by using mole concept and both by using equivalent concept. Okay, right. So we need, and if we want to apply the mole concept, we need balanced chemical reaction. What is the chemical reaction here? Barium chloride reacts with Al2SO4 thrice, that gives barium sulphate, barium sulphate plus AlCl3. That is the chemical reaction takes place between barium chloride and aluminum sulphate. But this reaction is not a balanced chemical reaction. That reaction is not a balanced chemical reaction. Okay, so if we want to balance this chemical reaction, that is this should be multiplied with 3 moles of barium chloride reacts with Al2S, 1 mole of Al2SO4 thrice gives rise barium sulphate. Okay, so that gives barium sulphate, 3 moles of barium sulphate, 3 moles of barium sulphate. Now it is a balanced chemical reaction. Okay, so first here the volume is given in ml, then we can calculate the millimoles. We can calculate the millimoles. Okay, so millimoles of the reactants before the reaction. So what is, how can we get the millimoles? Okay, now molarity multiplied with what is the barium chloride molarity here? 0.1. Molarity multiplied with volume in ml. Okay, volume in ml, that can give millimoles 20. Okay, and what is the molarity of aluminum sulphate? 0.2 into volume is 30 ml. Okay, so this gives 2 millimoles and this gives 6 millimoles. Okay, so and millimoles before the reaction, after the reaction After the reaction, this 2 moles of barium chloride, 2 millimoles of barium chloride reacts with the 2 millimoles of aluminum sulphate only. Already I told you 1 mole, 1 millimole, or when I was explaining the normality concept or equivalent concept, 1 equivalent reacts with only 1 equivalent. Okay, so here 2, but here that is not the concept. Okay, here 2 millimoles of barium chloride reacts with 2 millimoles of aluminum sulphate, but here 4 millimoles are extra. But why that 4 millimoles are extra? Because this wants to get reacted with the barium chloride, but there is no millimoles of barium chloride. So reaction is confined to 2 millimoles of barium chloride and 2 millimoles of aluminum sulphate. Therefore, this 2 millimoles reacts and the concentration becomes 0, and in this 6 millimoles that 2 millimoles are react with 2 millimoles of barium chloride, that remains 4 millimoles, and 2 millimoles reacts with 2 millimoles of aluminum sulphate, that gives 2 millimoles of barium sulphate, and of course it also gives 2 millimoles of AlCl3. Of course, we can explain this millimoles concept in a broader manner, but that is not required for this problem. Okay, so how many millimoles of barium sulphate is formed? 2 millimoles. What they asked? What is the weight of barium sulphate? How can we get the weight of barium sulphate? We know millimoles. We know the formula, that is millimoles. Millimoles is equal to molarity into volume in ml. Okay, millimoles is equal to molarity into volume in ml, and molarity means weight by gram molecular weight into volume in ml. Okay, weight by gram molecular weight. So weight by gram molecular weight into 1000, and how many millimoles we got? 2 millimoles. Okay, so 2 millimoles is equal to weight by gram molecular weight, then weight equal to 2 into gram molecular weight by 1000. Okay, then gram molecular weight of barium sulphate is 233. So 2 into 233 by 1000. Okay, that gives 0. You can calculate this fraction. That comes out to be 0.466 grams. 0.466 grams. Okay, so weight of barium sulphate is 0.466 grams. Okay, this is one method by which we can solve this problem. There is another method, and the another method is Milli equivalence method. Already I told you, when we want to apply the equivalence concept, there is no need of balanced chemical reaction. Okay, so barium chloride reacts with Al2SO4 thrice, gives rise to barium sulphate plus AlCl3. Okay, so now we shall solve this problem basing on the equivalence, Milli equivalence concept, because here the volume is given in ml. Okay, so Milli equivalence. Okay, Milli equivalence. We can get the equivalence or Milli equivalence if normality values are known, but here the given values are in the molarity. How can we convert the molarity into normality? Molarity into n factor, that gives normality. So, normality into volume, normality into volume in ml, that gives milli equivalents. Okay. So, here milli equivalents before the reaction, milli equivalents before the reaction. So, barium chloride, its concentration is 0.1 molar and its n factor is 2, and into how many ml? 20 ml. Okay. Next, here Al2SO4 thrice, Al2SO4 thrice, its concentration, its molarity is 0.2 and its n factor is 3 and its volume is 30 ml. Okay. So, 0.2, that gives 10, 1, so it was 4 milli equivalents. It gives 4 milli equivalents. It is to 6 milli equivalents. 6 milli equivalents. Okay. And it gives, it forms, so 4 milli equivalents of barium chloride reacts with only 4 milli equivalents of aluminum sulphate. Okay, that is the basic principle. Okay, milli equivalents react, 1 milli equivalent reacts with only 1 milli equivalent. Okay, already I told you when I was explaining the concept of equivalent. Actually, the concept of equivalent is introduced to comparing the reacting weights of chemical substances which are taking part in a chemical reaction, right? So, 4 equivalents reacts with only 4 equivalents. So, after reaction, the milli equivalents of barium chloride is 0 and milli equivalents of Al2SO4 is 2, and here how many milli equivalents are formed? 4 milli equivalents of barium sulphate is formed. Okay. So, here the milli equivalents of barium chloride is 4 milli equivalents limits the reaction. 4 milli equivalents of barium chloride limits the reaction, and that barium chloride 4 milli equivalents limits the reacting milli equivalents of Al2SO4. We have 6 milli equivalents of Al2SO4, but all the 6 milli equivalents are not allowed to participate in a chemical reaction. This limits, barium chloride limits the milli equivalents of Al2SO4 thrice. That is why this barium chloride is called limiting reagent. Okay. So, how many equivalents are formed? 4 milli equivalents. Okay. We know milli equivalents is equal to weight by gram equivalent weight into 1000. Okay. How many milli equivalents we have? 4. Weight that is to be determined. Okay, that is to be determined. Okay, weight by gram equivalent weight. How can we get the gram equivalent weight? Molecular weight by its valency for element, for its number of electrons transferred, for its oxidation state. Number, and in number of ways we can get the equivalent weight of a compound. So, gram molecular weight of barium sulphate or barium sulphate is 233. So, 233 by 2, that gives gram equivalent weight into 1000. Okay. So, in the next step 2 into weight by 233 into 1000. Okay. In the next step weight is equal to, weight is equal to 4 into 233 by 2 into 1000. Okay, which gives weight is equal to, which is also gives 0.466 grams. Okay, in these two ways we can solve this problem. So, in this problem we applied the concept of mole concept of mole and concept of milli equivalents or concept of equivalent weight. And the problem 2 is calculate the weight of calcium oxide required to remove the hardness of 10 power 6 liters of water containing 1.62 grams of calcium bicarbonate in 1 liter. So, from this problem we can understand that calcium oxide can remove the bicarbonates in water. Okay, so we should write chemical reaction. We should write chemical reaction. Okay, what is chemical reaction that occurs between calcium oxide and calcium bicarbonate? So calcium oxide reacts with calcium bicarbonate, CaHCO3 twice, that gives 2 CaCO3 plus water. Okay, so this is a balanced chemical reaction because number of calciums are equal and number of carbons are equal, oxygens are equal, and water molecule also equal. Okay, hydrogens are equal, oxygen are equal. Okay, so this is a balanced chemical reaction. From this chemical reaction we can understand 1 mole of calcium oxide removes 1 mole of calcium oxide reacts with 1 mole of calcium bicarbonate and to form 2 moles of calcium carbonate, right? Okay, so 1 mole of calcium oxide removes bicarbonates present in 1 mole of calcium bicarbonate, okay, to form in the form of calcium carbonates. Okay, by forming the calcium carbonates that can remove the bicarbonates in the calcium bicarbonate in the water, right? Right. So 1 mole reacts with 1 mole. Okay, here this is the balanced chemical reaction, but how many moles of calcium bicarbonate is here? In the problem they give what is it called, weight of calcium bicarbonate. We can get the weight of we can know the number of moles of calcium bicarbonate because they gave the what is it called, weight of calcium bicarbonate. Okay, calcium bicarbonate weight we can okay, we can know the calcium bicarbonate molecular weight. Okay, so 1.62 grams divided by its molecular weight, 1.62 grams divided by its molecular weight 162, that gives number of moles of calcium bicarbonate, that gives 0.01 mole, that gives 0.01 mole. So 0.01 mole reacts with already 1 mole reacts with 1 mole calcium oxide, 0.1 mole calcium bicarbonate reacts with 0.01 mole of calcium oxide. Okay, so 0.01 moles of calcium oxide reacts with 0.01 mole of calcium oxide. Okay, already it is for 1 liter. It is for 1 liter. It is for 1 liter. But here they asked us to calculate the 10 power 6 liters. They asked us 10 power 6 liters. So we should multiply the number of moles for this is number of moles for 1 liter. We should multiply with the 0.01 mole with 10 power 6 liters. For this is for 1 liter. Okay, so you should multiply the 10 power 6 liters. That gives the number of moles of calcium oxide which is required to remove the hardness of water in 10 power 6 liters. Okay, so you can get the this is 10 square, that is 10 power minus 2, that is 10 power 4 liters, sorry, 10 power 4 moles, 10 power 4 moles, 10 power 4 moles. Okay, so 10 power 4 moles required to remove the hardness of water in 10 power 6 liters of water, right? Okay, so 10 power 4 mole. So this is number of moles, but weight of calcium oxide is equal to 1 mole of calcium oxide weighs 56 grams. Okay, then 10 power 4 moles weighs 10 power 4 into 56. Okay, simply just multiply this equation with the 10 and divide with the 10. Okay, 56 divided with the 10, 5.6, and this is 10 power 4, this is 10 power 1, that is 10 power 5. 5.6 into 10 to the power of 5 grams of calcium oxide is needed to remove the hardness present in 10 power 6 liters of water. Okay, and the problem 3 is what volume of 0.1 molar KMnO4 is needed to oxidize the 100 ml of 0.2 molar ferrous sulfate, FeSO4 in acidic medium. We know that this is a redox reaction because KMnO4 is the oxidizing agent. Okay, KMnO4 is an oxidizing agent that is in acidic medium. We know the reaction that taking place in acidic medium. Okay, so 5 electrons plus 8 H plus gives rise to Mn plus 2 plus 4 H2O. This is the reaction that takes place in acidic medium. Okay, Mn plus 7 to plus 2, that gives 5 electrons transferred. Okay, and ferrous sulfate is an oxidizing agent, so Fe plus 2. FeSO4 is a reducing agent, KMnO4 is the oxidizing agent, that means that gains electrons. FeSO4 is a reducing agent that lost its electrons. So Fe gives rise to Fe plus 3 plus 1 electron. And already I told you, whenever the volume is in ml, okay, and we can solve the problem in a simplest manner, that is by using the equivalent concept. So milli equivalence of KMnO4 is equal to milli equivalence of FeSO4. Okay. How can we know the milli equivalence of KMnO4? We know the KMnO4 concentration 0.1, but it is milli equivalence. Okay, we should convert this milli equivalence, we should convert the molarity into normality. Okay, because milli equivalence concept is derived from normality. Okay, so 0.1 into how can we convert the molarity into normality? By multiplying the n factor. Here n factor is 5, so 0.1 into 5, and its volume is it should be calculated. Okay, and milli equivalence of FeSO4 0.2 into n factor is 1, and it is into 100. Okay, so V1 is equal to 0.2 into 100 by 0.1 into 5. Okay, so this is we can solve this problem 20 by this is equal to 40 ml. This is equal to 40 ml. So 40 ml of KMnO4 is required to oxidize the 100 ml of 0.2 molar FeSO4. And the problem 4 is 5 ml solution of H2O2 liberates 1.27 grams of iodine from an acidified Ka solution. What is the molarity of H2O2? Okay, what they asked, what is the molarity of H2O2? Okay, we should know, we should calculate the molarity of H2O2. What they given, H2O2 liberates iodine from acidified Ka. That means the number of equivalents of H2O2 that reacts with acidified Ki, the number of equivalents of acidified Ki, okay, or number of moles of acidified, number of equivalents, milli equivalents of iodine. So number of milli equivalents of iodine or number of milli equivalents of H2O2 is equal to number of milli equivalents of iodine, and it is equal to milli equivalents of K. Okay, so milli equivalents of H2O2 is equal to milli equivalents of iodine is equal to milli equivalents of K. Okay. So from that problem we can understand that milli equivalents of H2O2, already I told you, 1 milli equivalent reacts with 1 milli equivalent of one reactant reacts with 1 milli equivalent of another reactant. Okay, so in that way 1 milli equivalent of H2O2 reacts with 1 milli equivalent of iodine. Okay, so milli equivalents, how can we get the milli equivalents? Normality into volume in ml is equal to normality into volume in ml. Okay, but we don't know the normality, milli equivalents of I2, we don't know. We should calculate the, what is it called, molarity of H2O2. Okay, so we know normality, we know the normality okay, normality, we should find out the normality. First we shall find out the normality of H2O2. From its normality value we can calculate the value of molarity. Okay, so milli equivalents of I2, normality is equal to, we can write this equation as a weight by gram molecular weight by n factor into volume in ml, and that is 1000. Okay, so weight is equal to, weight, how much weight is they given? 1.27, and the molecular weight of iodine is 127 and its n factor is 2 and it is equal to 1000. We can get the this value 1.27 into 22 by 127 into 1000. Okay, and volume of H2O2 is 5 ml. When we calculate this fraction, that gives 10 by 5 is equal to 2. So normality of H2O2 is 2. So normality of H2O2 is 2. Okay, and we can get the molarity of H2O2. Molarity is equal to normality by 2. Normality is 2 by 2, that is equal to 1. So molarity of H2O2 is 1. So in this way we can apply the concept of mole and concept of equivalent weights to gravimetric analysis and as well as volumetric analysis. Okay, these problems, these type of model problems are very important in NEET, JEE Mains, etc., etc. Okay, thank you for watching.